All right, infinite series, or the sum of a geometric sequence. The sum of a geometric sequence is called a geometric series. In general, geometric sequences are infinite as the number of terms is usually not fixed. For a finite number of terms in the geometric sequence, we can consider the sequence a plus ar plus ar squared plus ar cubed, etc., all the way to ar to the power of n minus 1. The sum of those terms is defined by this equation. So the sum of the series of n equals a times 1 minus r to the power of n, all divided by 1 over r. And before we go too much further, let's make sure we can identify that in the sequence, a is the first term, r is the common ratio or the rate of change, and then n is the number of terms. Okay, so to find the sum of all of the terms in a geometric sequence, we have to look at the limit of the sequence as n goes towards infinity. So this is stating as the limit of n going to infinity of the sequence of n, we want to consider the rate part of this term. So we just want to look at this section here, r to the power of n. If the absolute value of r to the power of n, if r is less than 1, then this part of the function, so like for example, if it is 1/2 or negative 1/2, then both of these things will go to 0. And that means that we can evaluate the limit. In this case, this type of series is called a convergent series because the values of the series keep getting closer and closer to one number. Okay, and we can evaluate the limit. So let's have a look at this first example. So we need to identify all of the parts of this sequence. In this series, the first value is 1/2. And in order to go from 1/2 to 1/4, I must have gone times by 1/2. And I can check that again to see, in order to go from a quarter to an 8, yeah, that's times 1/2 again. So my rate is also 1/2. So now I can determine, I know that my absolute value of r is less than 1. So the limit as n approaches infinity, so as the sequence carries on forever and ever, the sum of this series is a over 1 minus r. A is 1/2, this 1/2, and my rate is also 1/2. And when I solve this, 1/2 divided by 1/2, excuse me, is just 1. So the limit of this sequence is 1. Okay. In the other instance, if the rate of increase or decrease is greater than 1, then the limit does not exist. Okay, because there is no limit of the rate to the exponent n. And then in this case, this is called a divergent series because the numbers keep getting further and further apart, and the series does not even have a definite sum. So like, let's look at this example. So in this example, in order to go from 3/2 to 3, I times by 2. In order to go from 3 to 6, I times by 2. If I were to do this again, I would have 12. Then I would have 24. And as you can see, this limit keeps getting bigger and bigger. My r is 2, which is greater than 1. So the limit does not exist in this case because I'm not converging, I'm getting further and further away. Okay, let's look at two other kind of obscure examples. So in this instance, I want to find the sum of this series. And the limit as n approaches infinity of this series is just a times n. And because I actually am not, this is just this same number over and over again, I know from my limit rules that I can move this a out front. So I'm just looking at the limit as n of n as n approaches infinity. Well, I know that that does not exist. So therefore this series does not have a sum either. Oops. So this is a constant as a series. Okay, what if r equals -1? So the rate is flipping back and forth between positive a, negative a, positive a, negative a. So this one is weird again, but different. So if the number of terms in this series is even, then the sum of that series will be 0 because I'll have an even number of pairs. But if the number of terms in this series is odd, then the sum of those terms will be a. And because these two things are not equal, oops, this limit officially does not exist as n approaches infinity. And those are just two weird examples, not the primary focus. Okay, let's look at some other real ones for practice. So we have the series 2, 2/3, 2/9, etc. The first thing to do is we need to identify our variables. So the first term is 2, that's easy. R is harder to see, so I need to think, how do I go from 2 to 2/3? What do I need to multiply by? And I can see that I need to multiply by 1/3, and I'm just going to double check, make sure that 2/3 times 1/3 is in fact 2/9, and it is. Now that I know that 1/3 is my R and that's less than 1, I can calculate the limit of this series. So the limit of this series as n approaches infinity, as this goes on forever and ever and ever, is a over 1 minus 1/3. Oops. 2 divided by 2/3, which is 3. If I were to write that out, that's 2 divided by 2/3, or 2 times 3/2. Okay, so that's how I get my 3. All right, let's try another one. Okay, here it is written in this notation. So I can pull out my A and my R from right here. So my A is 5/6 and my R is 1/6. That's just given to me in this setup. And I know that my R is less than 1, so I'm going to be able to determine a limit here. So the limit as n approaches infinity of this series, I've got my A value and 1 minus my R value. So I've got 5/6. Sorry, I'm going to write it divided by 1 minus 1/6 is 5/6. Keep flip change. The limit of this series is 1. Okay. We can also use this to help us figure out the fractional equivalent for repeating decimals. So first what we're going to do is we're going to write out 4.5 repeated as a series of numbers. So 4 and 5/10, and also 5/100, and also 5/1000, and this carries on. And when I write out 4.5 repeated, I can see that this is actually a series. And I can identify the A. And I'm going to start, this is the part of the series that's repeating. So my A is 5/10. And in order to go from one term to the next, I have to go up by a 10th. So the limit of this section of the series, just this part here, is 5/10 over 1 minus 1/10. So that's 5/10 divided by 9/10, which is 5/10 times 10/9, which is equal to 5/9. And then I want to plug this guy back into that as well, just because he always was there. So that's 4 5/9. Let's do another one. Okay, so I have a repeater of 0.321. First, I'm going to write this as some fractions. So I have 321 over 1,000. And then my next term is going to be 321 over 1,000 and another set of 3 zeros because I need to move it 3 spaces back. So that's 321 over 1,000,000. So my first term in this case is easy to find because I don't have any non-repeating parts. My rate is a little bit harder to find. I need to think about how many zeros I've added to go from here to here. So I'm going up by thousands. So the limit, as this series continues on, is 321 over 1,000 divided by 1 minus 1,000. Sorry, just saying. The limit as n approaches infinity is 321 over 1,000. 1 minus 1,000 is 999 over 1,000. Keep flip change. I can cancel those common factors. And so the limit here is 321 over 999. Okay, let's do one more. Okay, this one I have a non-repeating part, 0.12, and then I get into the repeaters. 3, 4, and remember the place values where this is coming from. And then 3, 4. And I need to add 2 more zeros there because I've moved 2 zeros back. Okay, so my A, part of the repeating pattern, is 34 over 10,000. My rate, I'm going up by 2 place values at a time, so I'm going up in hundreds. So I'm going to determine the limit as n approaches infinity. 34 over 10,000 divided by 1 minus my rate. And I'm just going to actually keep flip and change because I know this is going to turn into 99 over 100. So I'm going to flip that right now. In this case, I don't actually cancel out all of it. I can just get rid of some of it. So now I've got 34 over 9900, and can't forget to add in the preceding part of that series. And I add those together. Actually, let's put that as a fraction so we can actually add it properly. And I'm just doing that in my calculator. 611 over 4,950. Okay, for homework, you've got page 56, numbers 1 through 4.